Namaste students. Welcome back to second PUC physics class, that is moving charges and magnetism. In the last video we have discussed about solenoid and what is the expression for magnetic field inside a solenoid. So solenoid is a long wire and which is wound in the form of helix, and it is used to generate magnetic field. And the expression for the magnetic field inside the solenoid is B is equal to mu naught N into I. Okay. So, this is the expression for magnetic field inside the solenoid. So, this is a solenoid, right. Here we have large number of turns. So, N number of turns which are closely wound. These are the two free ends of a solenoid. When this solenoid has been bent into a circular ring, we get a toroid. That is, if the two free ends are bent in circular shape, then we get a circular ring like this, right. Here there are two free ends. If we connect it to a battery, then we get a circular ring like this. Okay. So, this is nothing but the toroid. So, toroid is a hollow circular ring in which we have number of turns which are closely wound. It appears like a solenoid which is bent into circular shape. Now, let us see what is the expression for magnetic field inside this toroid. So, toroid, how to define it? Toroid is a hollow circular ring. So, it is a hollow circular ring in which we have large number of turns of wire, right, in which we have large number of turns of wire which are closely wound. So, this is a toroid. I will draw the diagram. So, we have number of turns in case of a toroid. So, the large number of turns we have So, like this we have large number of turns. So, wire is wound like this, and the two free ends. So, this is a toroid, and the two free ends are connected to the external circuit. When it is connected to the external circuit, current I flows through the coil, right. So, here we have N number of turns, large number of turns are there. Each turn is considered as a circular loop. So, I is the current flowing through this hollow circular ring, or I is the current flowing through this toroid. Now, let us consider a point P outside the toroid. Similarly, I will consider a point Q within the toroid or inside the toroid, and so there is a point R here. Okay. Now let us see what is the expression for magnetic field outside the toroid, within the toroid, and at a point R using Ampere's circuital law. So using Ampere's circuital law, we can derive an expression for magnetic field inside the toroid. I hope all of you know about Ampere's circuital law. What it states, according to Ampere's circuital law, the closed line integral of B dot dl is equal to mu naught into IE. The closed line integral B vector dot dl vector is equal to mu naught into IE or I, where I is the current which is enclosed in the Amperian loop. So this is the expression for Ampere's circuital law. Let us use Ampere's circuital law here. So in order to use Ampere's circuital law, we have to consider one Amperian loop. Here toroid is a circular ring, so the loop must be closed, Amperian loop must be closed one. So you can have any shape. Closed loop means you can have a circle, or you can have a square, or you can have a rectangle. Here I will consider the circular Amperian loop because the toroid is a circular ring. Okay? If this is a circular ring, then it is better if you consider circular Amperian loop. Okay. Now let us consider the circular Amperian loop. I want to find out the expression for magnetic field outside the toroid. So here at the point where you have to find out the expression for magnetic field, you have to consider one Amperian loop. So this is the loop. Okay. So we know that the current carrying conductor must be inside the loop. So here this is the conductor which is carrying current. So this is the imaginary Ampere or Amperian loop, and the conductor is placed within this loop. So no problem. Now let us see what is the current, what is I. Okay. Now at every point, now you just consider this circular loop. The current is flowing like this. At every point, at this point, the current goes like this, and the charge carriers will move like this, and at this point the current will move or flow like this. Here, if you consider these 2 points, this is the current coming out, and this is the current which is going in. The amount of current is same amount of current is going in and coming out. If I consider this current as positive, so I will denote this as plus I. The current which is coming out is considered as plus I, and the current which is going in is considered as minus I. The quantity or the magnitude is equal, so these two will cancel out. For example, you just imagine that this is Amperian loop. Okay. I have a conductor. We know that I is the current flowing through the conductor. When current I flows through the conductor, around the space we have magnetic field. So this is a point P. So the distance between the conductor and the point P is R. So in this direction current is flowing. So, using right hand clasp rule, we can find out the direction of magnetic field. If this is the direction of current, then the curled fingers give the direction of magnetic field. So, at this point magnetic field is going into the plane of the paper, and at this point the magnetic field is coming out of the plane. So, this is the direction of magnetic field. Or if you want to find out the direction of magnetic field, then you have to draw one tangent at the point. So, if I is a current flowing through this conductor, then the current enclosed in the area is I. If this is the case, that is, if we have two conductors within the loop we have two conductors and both are carrying current in same direction. Okay. So, this is IA and this is IB. These two conductors are carrying current in same direction. So, in this case the net current I is equal to IA plus IB. This is when there are two current carrying conductors within the Ampere's loop, and if they are carrying current in the same direction, then the net current I is the sum of IA and IB. This is only when the conductors are carrying current in same direction. If the conductors are carrying current in opposite direction, one is carrying current in this direction and another conductor is carrying current in this direction, then the net current I is equal to IA minus IB. If the two conductors carrying current in different direction or in opposite direction, then I is equal to IA minus IB. If they are carrying same amount of current, then IA is equal to IB. In that case, I is equal to 0. So, this you have to remember, these 2 points are very, very important. So, this is one term. Okay. So, this is nothing but a circular ring. Here plus I is the current coming from the loop and minus I is the same amount of current which is going like this. Both are equal in magnitude or both are equal. So, plus I and minus I both are equal, so they cancel with each other. So, here also we have plus I and minus I. You can consider this as minus I and this as plus I, no problem. So, here I will consider this as plus I and this as minus I. Here also both are equal, so these two currents will cancel with each other. So, the net current through the toroid within this loop I is equal to 0, right. Therefore, at a point outside the toroid, closed integral B vector dot dl vector is equal to mu naught into I. So, the net current I is equal to 0, right. The net current, because the current entering in is equal to current coming out, both are equal, so they will cancel with each other. Net current I is equal to 0. If I is equal to 0, then the closed integral B vector dot dl vector is equal to 0. So, this is nothing but B dl cos theta, B dl cos theta. What is theta? Theta is nothing but the angle between B and dl. So, here the direction of B and direction of dl, they are in same direction. So, theta is equal to 0, cos 0 is equal to 1. So, B dl is equal to 0. Magnitude of magnetic field is same because all the points are at same distance from the center. So, B closed line integral dl is equal to 0. Here dl cannot be is equal to 0. Therefore, B must be is equal to 0. At a point outside the toroid, magnetic field B is equal to 0. Now, let us see at this point R, what is the expression for magnetic field? If you want to find out the magnetic field at R, then you have to draw one loop and we call that loop as Ampere's loop. So, I will consider one Ampere's loop or Amperian loop here. We know that the current carrying conductor must be inside the loop. Here there is no current carrying conductor inside the loop. So, I is equal to 0, magnetic field B is equal to 0. The current carrying conductor. So, this is the current carrying conductor. The current carrying conductor is placed outside this loop. Therefore, current I within this loop is equal to 0. Therefore, magnetic field B is also is equal to 0. So, at a point R, magnetic field B is equal to 0. Now, let us see what is the magnetic field inside the toroid. So, here what is the magnetic field? For that, consider one point Q inside the toroid. Okay. This diagram can also be drawn like this. So, this is one surface, this one. So, this is the second one, this surface. Okay. At this point, the current is coming like this. So, at this point current is coming like this and it flows like this. At this point current enters like this. So, the current is traveling along the conductor like this. So, at this point it is coming out. So, it is denoted by a dot. Okay. I am using a dot here because at this point or on this surface here the current is coming like this and after that it moves like this and at this point it enters in. So, here the current is coming like this, therefore, it is denoted by a dot. So, this is the direction of current. Okay. After this it will go like this and at this point it will go into the plane. If it moves into the plane, then it is represented by a cross. So, I will denote it by a cross. Okay. So, this is the difference between dot and cross. If magnetic field is coming out of the paper, then it is denoted as a dot, or if it is going into the plane, then it is denoted by a cross. So, this is same in case of electric field. Okay. So, here the current is coming out, so it is denoted by a dot, and here it is going in, so it is denoted by a cross. So, our Amperian loop, or we have to find out the magnetic field at this point, right. So, we are considering 1 Ampere's loop here inside the toroid and the point is here Q. So, this is outside the toroid, point P, B is equal to 0, I is also is equal to 0. Here at a point R, here also B is equal to 0, I is equal to 0. Let us see what is the expression for magnetic field inside the toroid. We know that we can apply Ampere's circuital law only if the current carrying conductor is inside the loop. So, this is our loop. So, the current inside the loop. So, these are the currents which are inside the loop, right. So, we have only this surface inside this Ampere's loop. So, this is nothing but the current going into the plane. Here also cross mark represents the current is going into the plane, current is going into the plane, here also current is going into the plane. That means the current is flowing in same direction. If current flows in opposite direction, then net current I is equal to 0. But here within this loop, the current is flowing in same direction, all are traveling or all are going in. So, the net current I is the sum of all the currents, right. So, using Ampere's circuital law, B vector dot dl vector is equal to mu naught into I. So, B into dl is equal to mu naught into what is I? I is the current which is going into the plane. Here also current is going in, here also current is going in. So, current is going in. So, we can add all the currents because they are in the same direction. If they are in same direction, then the net current is nothing but the total current. So, in one loop or in one turn, I is the current flowing, then in n turns, what is the current flowing? N into I. So, the total current I is nothing but N into I. In one turn, I is the current flowing. In n turns, how much current is flowing? Cross multiplication, N into I. So, B into closed line integral dl. So, dl is the small line element. On adding all the dl's together, we get this circle, right. So, integration of dl is nothing but circumference of the circle. So, circumference of the circle is 2 pi r, where r is the radius, is equal to mu naught n into I. So, B is equal to mu naught n into I divided by 2 pi r. So, this is the expression for magnetic field inside the toroid. So, mu naught is the permeability, I is the current, n by 2 pi r. So, we know that n is the number of turns per unit length, right. While deriving the expression for magnetic field inside the solenoid, we have used n, small letter n. N is the number of turns per unit length. In 1 unit length, there are n number of turns, right. So, in 1 unit length, there are n number of turns. Then, in L length, how many turns are there? N number of turns. So, n is equal to n into L. So, this is the relation between capital letter N and small letter n. So, here this n means number of turns per unit length. So, this n is the total number of turns. Here L is nothing but the circumference of the circle, because we are considering the circular ring. In case of solenoid, we have only the rod, right. So, therefore, we are saying that L is the length of the rod. Here L is nothing but circumference of the circle. So, circumference of the circle is denoted by 2 pi r. So, L is nothing but 2 pi r. So, N is equal to N into 2 pi r, or N is equal to, this N is equal to N divided by 2 pi r, right. So, N by 2 pi r is nothing but N. Therefore, B is equal to mu naught N into I, where N is equal to number of turns per circumference of the circle. Expression for magnetic field inside the solenoid and the expression for magnetic field inside the toroid, both are same. In terms of magnitude, magnetic field inside the solenoid is equal to the magnetic field inside the toroid. So, outside the toroid we do not have magnetic field, here also we do not have magnetic field, only inside this toroid we have the magnetic field, and the expression for magnetic field B is mu naught N into I. So, first you have to write the definition. It is a hollow circular ring in which we have large number of turns of wire which are closely wound. It appears like a solenoid which has been bent into circular shape. Consider 3 points. Consider 3 points P, Q and R respectively. At P, what is the expression for magnetic field? How to find out the expression for magnetic field? Using amperes we can find magnetic field. That is closed integral B vector dot dl vector is equal to mu naught into I. So, for this Ampere's loop, the current carrying conductor is this one. So, the net current or the current coming out of the wire is equal to going into the wire. So, this is plus I, this is minus I. So, the net current I is equal to 0. So, I is equal to 0, therefore, B vector dot dl vector is equal to 0, B dl cos theta is equal to 0. Theta is the angle between line element and B, they are in the same direction, therefore, theta is equal to 0, cos 0 is equal to 1. So, the magnitude of magnetic field is same. So, I will take that outside the symbol, dl is equal to 0, dl cannot be is equal to 0, that means B is equal to 0. Therefore, outside the toroid magnetic field B is equal to 0. At a point R, so at a point R, Ampere's loop, so this is the Ampere's loop. So, there is no conductor within this loop, therefore, I is equal to 0, magnetic field B is also is equal to 0. Now, let us consider the point Q. At the point Q, using Ampere's circuit law, the closed line integral B vector dot dl vector is equal to mu naught into I is the current enclosed in the loop. So, this is the Ampere's loop, Amperian loop within this loop. So, this surface is within the loop and this surface is outside the loop. So, you have to consider only this surface. So, on this surface the current is going into the surface. they are in the same direction. If they are in the same direction, then the net current is nothing but the sum of all the currents. So, I is the current. If I is a current flowing through one turn, then what is the current flowing through n number of turns? N into I. So, B vector dot dl vector is equal to mu naught n into I, where n is the total number of turns in the toroid. So, B into integration of dl, theta is 0, dl is the line element. On integrating all the line elements, we get this circular ring. Therefore, the total length is nothing but circumference of the circle. So, B into 2 pi r is equal to mu naught n into I, or B is equal to mu naught n into I divided by 2 pi r. So, what is this n by 2 pi r? So, we know that n is the number of turns per unit length. Here we have, instead of L, we have circle. So, n is equal to n divided by 2 pi r. So, n by 2 pi r is nothing but n. Therefore, magnetic field inside the toroid B is equal to mu naught n into I. So, the expression for magnetic field inside the solenoid is equal to the expression for magnetic field inside the toroid. So, take down. Only the definition and the final expression is important. So, this derivation is not there for the exam. Take down.